Okay, guys, welcome to your third video. You do not get a thumbnail video of me before we start because it's Saturday and I didn't feel like putting makeup on. So we are just going to jump straight to handout 3. Buckle up and get your number thinking caps on because we are going to do a whole lot of work with a new notation system that we will use throughout the rest of the semester. So let's go ahead and get started. Now, as you can tell just from the top of the handout, there is a chart that has a lot of numbers on it, underneath a lot of letter names. So this semester, we're going to be using a new type of notation for you guys called integer notation. It's a different way for us to label the 12 chromatic pitches. Now, there are a couple of features of integer notation that are unique and are different from our usual letter name or staff notation. The first of those features is that integer notation assumes complete enharmonic equivalence. Now, you know what enharmonic equivalence is from theory 1. With integer notation, we're saying that C sharp and D flat and B double sharp are all going to get the same label, and that is the integer of 1. Now that has some implications, especially for non-diatonic and non-tonal music, because like we learned, especially in theory 2, when we started really talking about chromatic harmonies and how they resolve, accidentals have a purpose in tonal music. Sharped pitches, raised pitches want to continue going upward. They want to resolve up, and lowered and often flatted pitches want to continue to resolve downward. When we decide to use integer notation, that equalizes all of that. So there's no tendency with these notes. They are just sort of existing. So C sharp doesn't want to go anywhere specific, neither does D flat. They are both just integer 1. Now you might notice towards the right-hand part of this chart, when we get to 10 and 11, we stop using numbers and we use instead the letter T and the letter E. That's honestly just that's just for clarity, because once we start writing integers, we don't want to get confused between, is that a 10 or is that a 1 and a 0? So to completely eliminate that option, we just use T and E. Now, on top of enharmonic equivalence, integer notation also assumes octave equivalence. So any A anywhere in the acoustic system on your keyboard, on your instrument, is going to be 9. They are all equalized. Now, what that does is it reduces the entire chromatic system, the entire pitch space, to just 12 distinct pitch classes. And pitch classes is in bold because that is a term that we're going to see a lot. So we're going to A, give it an abbreviation because it makes life easier. And B, we will utilize this term a lot in our discussions from here on out. Now, this next statement on the handout is, it might seem a little confusing at first. So integer notation works on a mod 12 system. All that means is that there are 12 labels, the number 0 through the number 11. And that is it. We take anything outside of that numerical range, anything outside of 0 to 11 is going to get reduced into that range. So let's say we have the number 13. That is outside of the range of 0 to 11. So how do we reduce that to fit in? We add or subtract 12. In this case, we would subtract 12. 13 minus 12 gives us 1. So 13 is equivalent to pitch class 1. Now, some of you might be completely comfortable just navigating that mathematically, and it might just sort of like make sense in your brain immediately. For some of us, especially if you're a more visual learner, this is where the clock face comes in. Now, at the back of your course pack, I have included a bunch of blank clock faces. That's going to be especially helpful in Unit 2, but you might kind of take one of those pages and earmark it and use it for reference until you're comfortable enough with the clock face that you can either pull it up in your mind's eye or sketch one really quickly. But if you take a look at this clock face, we use the clock face icon a lot in music theory. We talked about a 7-nodule one in my aural skills class the other day with modes. We use it for the circle of fifths. Now we're using it for chromatic pitch space. And so as you look at this, you see that the pitch C, also known as pitch class 0, is at the very top. And as you move clockwise around the clock face, we are just going up by semitone. So our integers are just going up from 0 all the way to 11 at the spot that would be 11 o'clock on the clock. Now, the reason that this clock face can become especially useful for this mod 12 system is it really reinforces the fact that you start at 0, you keep going. When you get to 11, keep going clockwise. 11 does not then turn into 12. 11 goes back. It rolls back over into 0, and then you keep on going. So the clock face is a nice kind of visual representation of that mod 12 system. Now we're going to do a couple of things with integer notation today to just get you comfortable with it. And after a while, you're going to find that you sort of automatically know certain pitches first. So a lot of us, it's going to be, okay, I know that C is 0, and you might know that F sharp is 6. And you sort of fill in the gaps as you work. So for right now, keep the clock face handy because you're probably going to want to use it, or even the chart at the top of the page. So what I'd like you to do, we're going to take the first 2 measures of this Debussy piece. And this is a piece we're going to listen to in class on Friday of this week. But I want you to just go through, grab a pencil, and label every single one of those notes with its proper integer. Do that and then come back and we will compare notes and chat a little bit. Okay, so compare your answers to mine. And there are a couple of things I want to just highlight. One is that as you went through, I do want you to make sure that you utilized the T kind of abbreviation for the B flats. So rather than labeling them as the number 10, you used T. The other thing to note is because of this enharmonic equivalence, you hopefully have called the A flat and the G sharp in measure 2 the same thing. So they are both pitch class 8, even though they are in different octaves, and even though they are actually written as 2 different pitches on the page, A flat versus G sharp, they are both still pitch class 8. Okay, let's move on to the second page. So we're going from labeling pitches now to labeling intervals. Labeling intervals with integer notation is simply a matter of counting half steps, counting semitones. Now, again, with this, we have complete enharmonic equivalence, which means that in this case, a major sixth, for instance, is labeled the same as a diminished seventh, an augmented fourth is labeled the same as a diminished fifth, etc. And again, this becomes really important for non-diatonic and non-tonal music because even interval sizes imply certain things, especially when we get out of the major and minor and we start talking about augmented intervals and diminished intervals. Those labels imply a certain level of direction. And we talked about this a lot in theory 2 and theory 3 in terms of resolving tritones in your chords, in your diminished seventh chords, in your dominant chords. We always said augmented fourths want to split outward and keep getting bigger, whereas diminished fifths want to collapse in and get smaller. Now, when we do away with those labels and we just call that interval class 6, all of a sudden there's no implied directionality to it. There's no implied role for it. It just is interval class 6. So let's do a little bit of comparison here. You've got the same excerpt of music. So what I'd like you to do is on the top line, you're going to write interval size and quality. So the first one, then you would label as a major third, etc. And then below the score, I would like you to note the same intervals, but as integers. So you'll likely then jump up to this chart, this very first one, major third, we see on the chart here, we would label that as 4. So go ahead and do the rest of this excerpt and then come back and check your work. Now, this likely seemed really boring for the first 5, right? So you've got a chain of major thirds. We'll go above the staff first. You've got a chain of major thirds. And then those last 2 dyads, those last 2 pairs of notes, are kind of funky looking intervals. And you might have had to kind of scratch your head a little bit for a second, but they are both diminished fourths. Why is that important for this discussion? Hopefully you have a chain of 4s on the bottom, on the line below this staff. The integers for every single one of these intervals are the same. The number of semitones is the same for every single one. Now, diminished fourth isn't on your table above, but a perfect fourth, one smaller, diminished fourth, which is equivalent in size to the major third. So you have this chain of 4s underneath the staff. And again, this really highlights the fact that just like on the first page, we talked about how the A flat and the G sharp got the same label. They were the same pitch class. Now we see how the major third and the diminished fourth, even though on the page they look like they are different sizes, they get equalized to the equivalent integer when we utilize this integer notation. Okay, so we've talked about labeling pitches. We've talked about labeling intervals. Now our last step is to talk about transposition. And this is where your head might start to hurt a little bit. So we use this label, T sub X, and this is going to start sounding a lot like high school math. And my apologies if that brings back terrible memories for you. But we use the label T sub X to show transposition of a pitch or a collection of pitches by any particular interval, with X being the interval itself. So X will be a number, and you have to apply that number to the pitch classes that you're working with. Again, there are 2 ways that are probably the quickest to do this. My people who are comfortable with math, just do the math. Remember that if you get a number that is larger than 11 or smaller than 0, you have to subtract or add 12 until you get a number between 0 and 11, because we're working in that mod 12 system. But if that math stuff is not for you, go back on the clock face. So say I tell you, let's say T5 of pitch class 10. 2 ways to go about this, right? So you've got pitch class 10. I'm saying T5, so you're going to add 5 to it. That gives you 15. That's more than 11. So you're going to add or subtract 12. We're going to subtract 12, and that gives us 3. So pitch class 10, if you do T5 to it, gets you to pitch class 3. That's one way to go about this. If that is not your jam, another great way to do this is, okay, she's asking me to do T5 to pitch class 10. So I'm going to come over here to my clock face. There's PC 10. I am going to move 5 spots on this wheel. So I'm going to go 1, 2, 3, 4, 5. That's where I end up. Same exact answer, virtually no math involved. So with that in mind, then, we are going to look at that same excerpt again. And I want to know what the transposition level is from each dyad to the next. Now, one thing I didn't mention yet is the transposition we just did on the clock face was a transposition upward. We moved clockwise around the clock face. It was T5, positive number. You can also go in the opposite direction, right? Just like normal transpositions, you can transpose upward, you can transpose downward. When you transpose downward, you are going to have a negative transposition number. So your transposition integer will be positive for upward transpositions and negative for downward transpositions. This is a lot of words. Let's go through the first one together. So we have this first dyad, and I'm going to go back to the first page, and I'm sorry if this is going to make you a little dizzy. But this first dyad, we labeled as 8 and 4. The second dyad, we labeled as 6 and 2. All I need to know is what you had to do to get from 8 and 4 to 6 and 2. So 8 to 6, 4 to 2, you had to subtract 2, right? So your transposition then for this first dyad is T negative 2. Go ahead and work out the rest of these. And remember, especially when you get to that second measure, that our intervals and our pitches are enharmonically equivalent. So when you start getting to the A flat going to the G sharp and the major third going to the diminished fourth, remember that all of that gets equalized in this notation system. So work through the rest of these and then come back and let's check our work. Okay, let's see what else you came up with. Now, hopefully you have a lot of similarities from one dyad to the next. Now, if I had asked you to just explain to me in layman's terms, in terms that you're comfortable with, what is going on in the first measure, most of you would likely say, oh, each pair of notes is moving down by whole step. The labeling system that we have here is telling us that same exact thing. So we have transposition down by 2 semitones. So at -2 is telling us we're moving down by 2 semitones. And we do that for almost the entire excerpt, right? The only time we don't is, unsurprisingly at this point, I think, the downbeat of measure 2. That's been the weird spot the entire time. So let's take a look at what's going on from this doubly dotted eighth note to this 32nd note. Now, the top half of this dyad, the C's, are a very obvious octave. But it's the bottom half of the dyad that's challenging. If I were to ask you to tell me in our major, minor, diminished, augmented labeling system what's going on, A flat going up to G sharp, you wouldn't be able to tell me that it's an octave, because actually on the page that is not an octave, right? You would have to come up with a different label for it, even though if I were to play it at the piano or on another instrument, it would sound like an octave. Now, luckily, integer notation just kind of equalizes that for us, right? We have an 8 and a 0 moving up to an 8 and a 0. So your T12 reflects that 12 semitone transposition upward. And then you have one more transposition downward by a whole step here. Okay, so if you're still with me, We are going to use this information to introduce what is, ironically enough, the easiest of the collections. So we took one of the more difficult and mind-melty topics, and we paired it with the easiest of the collections. And the reason that we're doing these together is we label the whole tone collections using integer notation. So when we are talking about whole tone collections, you've been looking at one for the last however many minutes. That little WC excerpt was actually a whole tone example. The whole tone collection is exactly what it sounds like. It is a collection that is generated by starting on any note and just moving up in whole steps. What's going to happen is eventually you're going to recycle and come out on your starting note an octave up and just keep playing through the same collection of pitches. We have two whole tone collections, and they divide the chromatic. Each collection divides the chromatic system in half. So you have one collection that takes up 6 notes, and the other collection uses the other 6 notes. So they are complementary collections, just like the diatonic and pentatonic collections are complementary of one another. Now we have two whole tone collections, and we refer to them as even and odd. And that is because of the pitch classes that they contain. The even whole tone collection contains all of the even numbered pitch classes. We also label that and refer to that as the collection whole tone 0. And that's just because it contains pitch class 0. Now, on the flip side, then the odd whole tone collection contains all of the odd numbered pitch classes. And we label this collection whole tone 1 because it contains pitch class 1. So what I'd like you to do is on the staff, you're going to notate and label each of the collections. So I'd like you to write out a whole tone 0 collection and a whole tone 1 collection and label them each. Now, it's free choice for whether you use sharps or flats or whatever kind of funky things you want to do. As long as you have the correct 6 pitch classes, you can notate them however you want. Try and keep it from being like super weird, but hey, go to town. So go ahead and write out those 2 collections and then come back and check your work. Okay, now we might not have the same exact notes on the page. You might have a G flat for the 4th note of your whole tone 0 collection. But as long as our pitches are enharmonically equivalent, then we're good to go. Another way to kind of double check yourself is jump back on the clock face. But I'm going to write the pitch classes below each note just to kind of reinforce what we have going on. So C is pitch class 0, D is 2. Don't forget to label the B flat / A sharp as a T. And then I'll do the same thing with the odd collection. Now I'm going to bring us back to the clock face one more time before I wrap up. Let's say that I want to map the even whole tone collection on the clock face. And to do that, I'm just going to draw little kind of nodes on all of the pitches. Now, if you look at the way that that parses itself out on the clock face, if I were to divide this clock face this way, or quite frankly, anyway, you would find that this system is symmetrical. So if I were to put a mirror right here, the collection would look the same on either side. The whole tone collection is a symmetrical collection that has a lot of implications for its sound. And for those of you who are thinking about composing for your capstone, you can keep that in mind, especially as we listen to our whole tone pieces this week. Last thing I'm going to mention is there is no free write for Wednesday's class. We are going to just kind of keep working on this and massaging it. We will use a piece, but it's a really short one. It's more for an exercise than it is for any sort of deep class analysis. But you will have a worksheet that you may hand in if you would like. So there's going to be a worksheet on Blackboard that you can do. It's in conjunction with what we did here today. And that is due at class time on Wednesday if you would like to hand it in for 5 points. If this totally made your head hurt and you have no idea what is going on, please come to office hours or make an appointment with me. If you're listening to this on Monday, I do have office hours at 4 o'clock Eastern time today. So feel free to come by for those. All right. Thank you guys, and I will see you in class.